Hello, I'm Hannah Mansfield, and this is my Physics 2212 Lab 5 lab report on the Faraday's Law lab. The purpose of this lab is to explore Faraday's Law by observing the interaction between a magnet falling and the roll of aluminum foil, and then to explore this relationship computationally through the use of GlowScript. The physics principles in play are Faraday's Law and the Biot-Savart Law. The Faraday's Law gives us a formula for flux, which is the magnetic field at a location times the area of one loop. The EMF, which is the change in flux over the number of loops, and then as always, as a part of it, volts is equal to the current times the resistance. The Biot-Savart Law gives us a way to measure magnetism of a rod over the length and desired radius of said rod due to the material it's made out of. This will prove useful in calculating the magnetic field of the magnetic field at the location for our aluminum foil. So for the experimental setup, we marked the north pole of the bar magnet. The second part is recording the video of the magnet being dropped down the tube while holding it in mid-air so to allow the magnet to drop out the end of the tube. We record 5 drops this way, and then scrub through the video to find the lengths of the times that it dropped, and then find the average of the times. Over here, I have my trials 1 through 5. As you can see, the average was 1.18 seconds per trial. Here's some other data I collected. The length of the tube is 0.3 meters. The width of the foil is 0.01 meters. The radius of the tube is 0.023 meters. The mass of the magnet is 0.023 kilograms. The mu found from lab 3 is 3.2 amps times meters squared. The average time taken in my physical trials was 1.18 seconds. However, the computational time was 1.214 seconds, and I'll discuss some of the disparity in my GlowScript code. So here are my aluminum foil measurements. I put in the aluminum foil measurements into my GlowScript code. I also used the magnetic field function of a bar magnet as used in lab 3 here as well in order to calculate that magnetic field as we talked about earlier with the Biot-Savart equation. And then the magnetic flux function as talked about earlier is also in here in order to calculate it. So then we found the ring and the current, that's the individual flux over the radius of the ring as we talked about due to the area. The magnetic field at each ring is then calculated, so we basically do a derivative where we're just calculating it at each step, and then we add them all together to find the magnetic field for each velocity and position of the magnet, and then getting a total computational model that plays an animation that looks like this. The blue lets us know that our flux is counterclockwise to the magnet, and it's just spinning around the magnet counterclockwise. As you can see, our velocity versus time graph, the magnet starts going really fast when it's only affected by gravity, but slows down a tad when the flux is playing into play, and then speeds up again once it exits the tube. The time in seconds, as talked about earlier, is 1.214 seconds, and the reason for this disparity could be due to calculative errors in the formation of the GlowScript code, as the equation was giving me some trouble in the later sections of the formula. So what if the resistivity of the conductor was reduced as close to possible to 0? How would the dynamics of the falling magnet change? So if the resistivity was reduced closer to 0, like getting infinitely closer to 0, the magnet would fall slower and slower. Eventually, if the resistivity was resized all the way to 0, the magnet would just stop completely somewhere in the tube. The induced current would also be larger, hence leading to that magnet being stopped due to the force pushing it upwards from gravity. And then what if the holes or slots were cut into the tube? How would this affect the rings currents in your model? If the holes were cut into the metal, the magnet would fall faster and it would reduce the number of rings / metal that would be affecting the magnet in the model. This would lead to a reduction in current. Thank you so much for your time. Have a great day.